Good morning or good afternoon, depending on where you're located. My name is Rick Dye. I'm a Key Account Manager for Teledyne Isco, specializing in flow meter products. Today we're going to introduce you to a very exciting new product that we just released that we feel will be a new paradigm shift in really the measurement of open channel flow. We're very excited about this. Traditional measurement technologies or techniques, I think would be good to review some of those before we get deep into the new technology. In the past, people have used primary devices, which commonly known as flumes or weirs. These are hydraulic structures that both shape and kind of control the flow going through this device. The big benefit of these is that you really only needed a level device to do a level to flow conversion. That's the way they work. And they were typically tied into a flow meter device. This is a flow meter on the right-hand side, many of you may be familiar with, which is a Model 4200 series flow meter. Different level measurement techniques currently available, or previously available as well, were bubblers, ultrasonic, and pressure sensors. Some of the advantages of using a device such as a flume was that they're typically viewed as a 5% accurate device. They're traceable. One of the reasons they are is because they could compare to an ISCO Open Channel Flow Handbook, which many of you have had, known as the Bible of flow measurement in the wastewater world. What was nice about that was you just simply took a level measurement, pulled your ISCO handbook out, looked at your primary device table, and made sure that the meter was reading the correct value. The problem with that is all it really did was tell you that the meter was doing the math correctly. It didn't really guarantee that the flume was working properly. This has been an accepted measurement practice for years. Flumes have been around for a long time, and they are considered one of the standards. Some of the disadvantages of flumes, though, they can be expensive. You have the cost of the primary device itself. You have the installation cost. Sometimes they were impractical to install. No place to install. In my years at ISCO, I've had multiple calls where people said I need to be 5%, but I cannot install the primary device. Well, then your hands were kind of tied, so a lot of times they were not very practical. You had head loss issues, debris. You're backing up the water a little bit, so you can have issues regarding those. Site conditions. This is another example of a potential problem. Flows can exceed the initial design specifications or requirements. Area of town may have only needed X amount of flow. Now they've grown past that, and you'll have submerged flow conditions through a flume. And on the opposite end of that spectrum, you've had people that would design for handling future flows, and the flume is actually not operating in its accurate flow range, so it's reading too low. Weirs. Weirs are very simple devices. You have a number of different types, but basically it's a dam that's installed in the flow. Measuring the level over it, we can calculate the flow rate. Construction can be very simple a lot of times, very easy to install. Primary device cost is typically a little bit lower. You're looking at a lot of times stainless. Sometimes people will use some other steel or even plywood we've seen. Requires only a level measurement to get an accurate reading. Some of the disadvantages of a weir, though, they can be expensive depending on the size of the weir and what it's made of. You have the construction and the installation costs as well. Primary device could be made out of stainless steel, which could be expensive. And you have head loss. You're putting a dam in the water, you're damming the flow up. That can catch debris, silt, and things like that. And if there are submerged flow conditions, this device will not work very well either. You need also proper hydraulics. I need to have the right amount of flow in order to flow freely over that weir. One of the things that ISCO has that I think is a unique advantage for us is we have a fairly extensive flow measurement lab. For those of you that haven't seen it, I thought I'd throw these pictures in. We can test in pipes anywhere from 4 to 24 inch and do a lot of different, a variety of different flow conditions to both help with design as well as testing the capabilities of our products. Is we want to provide the right product for the application, which is really the reason that Teledyne Isco provides so many different types of level or flow measurement technologies. I'll go through some of these briefly, but we do, again, want to provide the right product for the application. Many of you listening are current 2150 users. 2150 is a device that uses continuous wave Doppler to measure the velocity. We have a sensor that's mounted in the bottom of the pipe, transmits a 500 kilohertz frequency, measures the Doppler shift off the particles, and calculates an average velocity. This is basically what we're looking at if you were able to look at the spectrum of information. We look at what's coming back. We focus in on the center point of or really where we're getting the meat of the data, and we calculate an average velocity based on that. One area that ISCO has really improved on over the past few years is not only providing you good quality data, we now provide you with a lot of diagnostics information to be able to help you determine if your meter is working properly or not. In this case, here's an example of a site that was working quite well. You can see based on where I have the circle, some of the diagnostic information there was showing the velocity signal and the velocity spectrum information. You can tell by this information that we were starting to have some problems with this contact sensor. We are one of the few that will provide you this information to give you early warning of debris issues even with a contact device. One of the areas that we saw a need for a product was in large pipe applications, which is, some of you may be familiar with the ADFM, which is acoustic Doppler flow meter. The acoustic Doppler flow meter does what's called velocity profiling. 4 crystals on the top of that sensor will actually read the entire velocity distribution or profile in fairly large pipes. This is another area that we have used a lot to verify our existing equipment accuracy, and something that you'll be seeing in my presentation comparing to. So contact sensors were typically, historically, the only method for measuring flow without a primary device. They required a Manning formula in the old days, and it used only a level measurement to get that flow rate. Bubbler was one of the more common ones. Another one, I realize this is a non-contact device, but I included it anyway, is an ultrasonic and a pressure sensor. Then came along the area velocity measurement techniques. They provided more accurate data, and they also were able to handle surcharged flow conditions. Followed the Doppler area velocity sensors, which really improved the reliability of the existing AV sensors. And but the only problem with that was you still were a little bit uncertain about your data quality. Small pipes were also a challenge. You had sensors that could be obstructing the flow. We've seen that before where you have a hydraulic jump. But they also can collect debris and could be, again, hydraulic issues. Here's an example of a sensor, and I don't care whose it is. It's probably not giving very good data because of the debris on that sensor. There was a market need out there for a device that was a non-contact measurement system, needed more accurate non-contact than a basic ultrasonic, again, which used a Manning formula that could be plus or minus 20% or much worse. Could not handle surcharge or submerged conditions. So the first system that were available out there was a non-contact area velocity flow system, used a non-contact surface velocity measurement, a non-contact ultrasonic depth measurement. The advantages was more accurate than a level-only device. It was above water installation, which provided and allowed for minimizing the maintenance requirements. Some of the limitations, though, were installation, potential errors involving installation if it wasn't installed correctly. There's also, anytime you use an ultrasonic, you'd have a potential for a deadband error, and you need an additional device for measurement during a surcharge condition. This device requires, to do it properly, a velocity profile calculation, which requires manually profiling the site, which is not practical typically in widely fluctuating flows or during storm events. Bottom line is they only read the surface of the water. ISCO Teledyne solution is the LaserFlow. The LaserFlow is a non-contact area velocity flow measurement system that uses an ultrasonic to measure the water level and uses laser to measure the velocity. How does this work? Theory of operation: we have a sensor that's mounted above the water. It transmits using an ultrasonic, measuring the depth. Based on that water depth, it focuses the laser, you guessed it, below the surface. Another way of looking at it is we have our ultrasonic, we measure our depth, Based on that depth, we know where we need to look to get an accurate velocity, and we focus the laser below the surface. We now get a intense reflected energy back to the laser. We also have signals that get scattered in different directions. What we are interested in is really what's getting reflected back to the laser. This area is considered to be the converging section or point of convergence. We take 5,000 spectral velocity readings with every reading that we take. How do we do it? How do we set this up? There's multiple ways of doing it. This is the most common or easy way to set up, I guess. The most common way would be doing a simple ultrasonic depth measurement. We focus the laser below the surface, and this is known as a single point velocity method, very commonly used. We also have the ability to do multi-depth velocity, which we take a depth measurement. You turn on the laser, and we focus the laser at 3 points on a vertical plane in the center. That's referred to as a multi-depth velocity method. We can also do a multi-point velocity method, and the way this works is we take a depth reading using the ultrasonic. We now turn on the laser, and we are able to read 5 points across a horizontal plane below the surface of the water. What's key about this one is if you have a non-uniform channel or something that's maybe not perfect hydraulics, the laser will tell you what it sees at different points in that horizontal plane. This is referred to as the multi-point velocity method. Then we took it one step further and we said, that's wonderful, but what if we were able to do a level measurement, and let's turn on the laser, let's do a horizontal sweep, but let's go below the surface even further, and we can actually read 3 points below the surface at 5 points across the horizontal plane, giving us 15 points of velocity. This is referred to as a multi-point, multi-depth velocity method. So when would we want to use a single point measurement? If I have uniform and consistent flows, I would probably be fine using a single point reading. If battery life is a concern, these can be used both, and I will explain later, but both in AC and DC powered applications. When we take a reading, obviously it's going to consume energy. The more of those points you take, the more battery you would consume any portable application. Rapid data rate. When we take a reading, that takes about 15 seconds to take that velocity point. Our minimum reading interval would be about 1 minute. So again, if I want to take 15 readings, I'm not going to be able to get those in a 1 minute data storage rate. When would we use multi-point velocity? Well, multi-point, if we have non-uniform flows, so my flow is fluctuating all over the place, and I want to see what's going on there, I can turn the laser on and see each individual point while I'm at the site and determine which laser point I want to look at, or I can leave them all on. If I have AC power, now we really don't have a concern about battery, and maybe it's a billing application, you want to get the most data you can, the highest accuracy possible. You may want to turn all of those points on. Longer reading intervals. Maybe I'm okay with 15-minute readings. I don't need 1 minute reading. Okay, let's turn all those velocity points on. Okay, the next major change we made with comparing to some of the technology currently available was submerged flow conditions. When we have a submerged condition, how are we going to handle that? If the laser is underwater, it will not read. So we needed to have a method of measuring that submerged condition. The way we accomplish that is with what we call a TINET, which is Teledyne Isco Environmental Network Continuous Wave Area Velocity Sensor. It is mounted on the bottom of the pipe, as shown in the picture there, facing basically down. It's just inverted from the way it would normally be on a ring in a pipe. We use the same proven technology that we've used in 2150s and our area velocity equipment now for a number of years. It will give you a wider measurement point than some of the single velocity methods that are available. We're now looking not only down into the flow, but a wider path of the flow itself. The measurement of this, which is nice, is we can actually leave that sensor off, not consuming any power, but it can check its level periodically, see if there's any water hitting that sensor at all, based on a pre-programmed condition. Once the water actually hits that sensor, then we turn the velocity sensor on and we start taking velocity reading. So, to give you a little better understanding of how it actually works, our sensors humming along there, we have a ultrasonic measurement taking place. The sensor's mounted at the bottom, and we're reading laser velocity. One thing to point out is that we have a single cable from this device. This laser is another smart device, again, Teledyne Isco Environmental Network smart device, that allows for a single cable to be plugged into the laser with your sensor, but there's also only one sensor cable that goes all the way to the top of the manhole. You don't have a bunch of cables in there to worry about. So normal operation, it's using its ultrasonic level measurement, taking its reading. It fires the laser, looks below the surface to get the appropriate velocity reading. Now our water comes up. We are starting to become submerged. We're still getting an ultrasonic depth reading. The laser is still reading, but now we turn on our continuous wave velocity sensor, and we are completely submerged at this point. We now have the continuous wave sensor reading velocity, and we have the pressure sensor on the continuous wave sensor reading the level. Note that that sensor can read up to 30-foot submergence at that point as well. So you will get a good, accurate submerged level reading in your manhole in addition to accurate submerged flow conditions. Okay, we can also take that sensor and we can use it in a redundant measurement fashion. We can take the sensor, instead of mounting it on the bottom, we have cables as long as 23 meters that can be routed down into the flow stream or into the pipe if you wanted a second opinion. We can also take that sensor and mount it in another pipe in the same manhole. This will again read the depth using the ultrasonic and the laser reading the velocity. But independent of that, we have our redundant measurement sensor reading its own level and its own velocity in that channel. This system is very easy to adapt and very flexible. Down the road, let's say initially you didn't anticipate having any kind of submerged condition, or maybe didn't require redundancy. You decide down a few months later, wow, we really need that. It's easy to install that sensor. You just have to remove 6 Phillips head screws. The sensor will mount directly to the connector, which is an area velocity snap-on connector, similar to what we use on our 2150 sensor. So it's a very easy, adaptable device if future needs dictate that you need to do something like that. Okay, how do we get our level reading? We use an ultrasonic level sensor mounted in the back of the sensor itself, of the LaserFlow sensor. It has a range of 0 to 10 feet. But what we've done is we've actually designed it to deflect off a 45-degree plate that's part of the sensor mount itself, or the sensor itself. What's key about that is when we reflect off that 45-degree plate, we now have a 0 deadband. We have taken the deadband that any ultrasonic will have, and we've eliminated it from our level reading. Once that water level hits that sensor or hits the LaserFlow sensor, we are now turning on the continuous wave pressure sensor and no longer need the ultrasonic. In addition to this, it should be noted that the sensor mount and the way we mounted it is to keep moisture from condensating on a horizontally mounted sensor. So we can shed any moisture droplets or possible debris that could want to set on that sensor. So we've now, again, improved the maintenance, minimized maintenance requirements. So how do we install this? It's a very easy install. There are 2 bolts that mount a mounting bracket to the wall. That's one way of doing it. The laser can be installed both upstream and downstream. This time I should point out this device is capable of reading bidirectional flow. It is able to read either positive or negative velocities, which is a kind of a leap over current technologies. What you need to do is center the bracket over the flow screen to mount it. Here's a couple of pictures that kind of give you an idea. We have the LaserFlow sensor on the left. It's mounted in the middle of the channel. The right picture you'll see is showing the actual laser dot in the water. When you install that, again, install it middle of the pipe, parallel to the water surface. But one of the neat features behind this device is we were able to turn the laser on when you do the install. So now when the field crews go and install this, they can mount the device, get it centered, fire the laser. They can see exactly what the laser sees. They don't have to guess what it's seeing. They know exactly where it's pointing. So the other part of the laser install that's somewhat critical is we want to make sure the sensor is level. The level is indicated by a little bubble level on the top of the laser sensor. So field crews go out, they make sure they're aiming in the middle. They can adjust the pitch and roll to make sure that the level or the bubble level is showing that you are level. It should also be noted that the laser sensor has a accelerometer built into it, so remotely looking at diagnostics, we can tell, or you can tell, if the sensor is mounted correctly without even looking at it. Now, this is what the wall mount looks like. It also is used as a street level installation device. Now let me show you how this works. We have street installation tabs. Sensor cradles onto that sensor or the mount and snaps in place. What these alignment tabs do is allow for us to use a street level tool to install the device or remove it for periodic maintenance. Very easy to do. Just simply nestle that device on there and turn the handle, snap it in place, and it's locked in and ready to go. It should also be noted that once the unit is calibrated, the water level is calibrated, which is the only requirement. If you remove that sensor and you put it back in the same location, there is no additional level calibration required. It will take off right where it left. What the device looks like, again, the alignment tabs help you feel its way down into the mount if it's a deeper manhole, and you'll see the mount on top, 1/8 of a turn, and it snaps and locks the laser in place. What the laser looks like when it's mounted, again, it can be pointed into or away from the flow. It doesn't care which direction it's measuring that flow. Another method of installing the device or mounting it would be using a temporary spreader bar. This is basically a jack stand device that has spikes on the end that allow you to jack it against the walls of the manhole and make it so it gives you a good sturdy mount, but you can remove it without or install without having to drill any holes in your manhole. So the LaserFlow sensor, again, it's a TiNet, Teledyne Isco Environmental Network trademark sensor. Uses laser to penetrate the flow stream. We are not doing a surface velocity, we are penetrating the flow. We are the only ones that are able to give you a multi-point measurement below the surface. This technology is also capable, again, of reading bidirectional or positive or reverse flows, which is a significant improvement. It uses also a smart Teledyne Isco Environmental Network contact ultrasonic level measurement system. Because of the mount and the way it was designed, we have no deadband on that ultrasonic sensor. Mounting, again, being perpendicular to flow, will avoid any condensation that could potentially build up on a horizontally mounted sensor. So what are some of the capabilities as far as electronics that we can connect to this device? We have, you'll be happy to know, for the 2100 customers out there, we can hook to a 2160 module, which is a new module. or we can hook to the signature flow meter. So for portable installation, you can use the 2160, and for those of you, again, that are familiar with the 2100 system, it is a 2100 series family member. Same connection, same communication cables, the whole bit. It's a modular design. I can connect multiple 2150s if I want. So if I had a site that I had 2 or 3 other 2150s measuring flow in different pipes that feed into a manhole, and perhaps I had a larger pipe that exited the manhole, you could mount the laser on that system, pointing it downstream and measuring the combination of those lines that feed into it. So it's very flexible with existing 2150 users. Uses, again, a very power-efficient electronics, which run from anywhere from 12 to 24 volts DC. Because of the 2100 design, we can stack additional battery modules to extend the battery life. Keep in mind, the batteries that we use are non-proprietary ISCO batteries. They're not proprietary ISCO batteries. They are off-the-shelf alkaline lantern batteries. This is an important feature when you don't have to get in there and do any kind of sensor cleaning. Because it is part of the 2100 series family, it does the variable rate data storage. For those of you that are not familiar with this feature, this is one where we can actually adjust or modify the data storage reading based on a condition. Very commonly in the U.S., 15-minute readings are what people will select for data storage. But during an event flow or a storm flow, you may want to have the meter switch to a 1-minute high-resolution mode, in which case it will be taking 1-minute readings when that event happens. Once the event goes away, it now back shifts to the 15-minute mode. This is an extremely popular feature with 2150s, and we feel it will be another very positive feature for the LaserFlow. It uses the same interface and communication options, which means it is FlowLink compatible. There is an upgraded FlowLink version to connect to the laser, but the only other thing is that's really all you need. Communication cables work the same. The cellular communications work identical, as well as the FlowLink Pro push capability. So it fits very nicely into the existing 2100 series family. Permanent applications. We have the signature flow meter, which is a permanent meter that is AC powered. It has the capability, because it is a smart device, to use or to handle multiple simultaneous inputs and outputs. For easy field upgradable options, such as analog outputs, multiple ultrasonic sensors, area velocity, continuous wave sensors, as well as the laser. So it's a very user-friendly, upgradable product. Data integrity. The signature has the ability, when it stores data, that it will allow you to use a program to verify that the data has not been altered in any way. And this is extremely important for billing applications or even custody transfer applications where data integrity is key. We have also added a USB interface option so that now you don't have to have a laptop to download. You can simply plug in a USB interface and download the data. As the same with the 2100 series, it has the variable rate data storage capability, which will be key, again, I think, in a lot of billing applications where maybe they run different shifts and they have more flow during the day than they have at night, and they want to capture more data during the operation of that facility. Has the ability of using an integral cell phone option or Ethernet communication option. And yes, it is FlowLink compatible. This is what the signature looks like. It has a built-in display as well as the keypad programmability. So to give you a little better idea of the flexibility of this device, we have internet accessible data, different alarm configurations, USB options, again FlowLink, Modbus, SCADA, Ethernet, or analog. On the flip side, we can interface to a sampler for pre-treatment. We can connect to anything in the TiNet family, such as multiple ultrasonic level sensors, multiple bubblers, SDI-12 inputs, as well as different devices that may have a Modbus output. We can take that directly in as well. And yes, as well, we can connect to the LaserFlow sensor. So we look at some of the data. This is an application where we have a 48-inch pipe being compared to a ADFM, which again is the acoustic Doppler device. And the ADFM is specified to be a 2% accurate device. If you look at the data in great detail, what you will notice, this is, by the way, FlowLink software, the top pane is the level data. What I have done here is I have the level of the ADFM in blue, the level of the laser is in red. As you will note, they are a mirror image of each other. In FlowLink, we also show you the average for the time period being displayed, which is 16.21, 16.57 on the ADFM. Very, very tight. The second pane is the velocity. Again, blue being ADFM, red being laser. The average level or velocities are, again, very, very close. And the subsequent flow rates compared to each other are, again, a mirror image. You will see that this device is, in this application, was within 5%. This is a 48-inch line, or excuse me, 0.5%. Here's an application where we had a test meter in the city of Omaha. You have your normal diurnal pattern. Again, we're looking at the level. This is the laser only. You have level data here, looks very normal. What's interesting with this data is we have a couple little bumps that were different than a normal diurnal pattern we were looking at with normal open channel flow. And we would see these little blips periodically and couldn't really explain them. We talked to the city of Omaha engineers. They said, oh, wow, that makes perfect sense. This is upstream from a siphon, and you can literally see the water surging as the site conditions downstream change during the time of the day. So very interesting that the laser was able to pick up such fine detail on that location. As the ADFM, again, we had the ability of comparing to a good standard in a 72-inch line. This is the ADFM compared to the laser. The top pane, once again, is the laser in red, ADFM in blue. The velocity, again, in the center here. And they had a nice storm event. What you'll see is a pretty significant submerged flow condition or surcharge condition. Level went anywhere from about 12 to 50 plus inches. The laser tracked all the way through that, very, very close. Keep in mind, this was a single point velocity method. We didn't even use a multiple point on this, and it did a very good job. What you'll look at is when you look at the totalized flow, 524 versus 526 million gallons, there was a difference of less than 0.5%, 0.36% in this case. Okay, when you're doing non-contact, it's important to have something that you don't have to obviously do maintenance on, but you don't want to have to go and recalibrate, and you want to make sure you have good, stable, reliable, daily repeatable data. This is a site in St. Louis where they were testing. This is a pumped flow application, and you can see it in the level data as well as the velocity, but you'll see the up and down trend with the pumps kicking on and off. The bottom pane is actually the two different velocity days shifted over each other. So I took one day normal and shifted it over the other day. What you will see here is an extremely repeatable pattern. The velocity for these two days, the average was 1.966 and 1.962. Incredibly stable and reliable velocity information. Here's another site, again, where we looked at measuring not only the depth and the velocity, which are in panes 1 and 2, but we, again, are capable of reading and storing a lot more diagnostics information. When you look at this, our level and velocity look very normal. The two panes on the bottom, which are pane 3 and 4, this one shows the ultrasonic signal strength. So now we can verify and ensure that the sensor is working properly from a level standpoint. This is all stored in the data storage. You can alarm off of this condition to know if somebody were to have to go do any kind of maintenance on this location. What's even more key is we store the return laser signal power, or the energy. This is huge because anytime you're doing non-contact, you have to know and you have to have confidence in the reading that you're getting is valid. We will be able to tell you, or your meter will be able to tell you, if what it saw was a valid reading and what it saw it liked. So now you can not only do in-pipe readings where you have verifiable data using diagnostics, but now you can do non-contact, getting the same powerful information to be able to confirm your data are correct. Okay, so where would we use this device? Collection system monitoring would certainly be one of the applications. We have permanent AC powered signature, so some of the major trunk lines that might need to be permanently monitored could be easily adapted using a signature meter. These can be used for billing applications in those types of devices where maybe custody transfer is a big one. We can also do portable DC powered, as I discussed, using a 2160. This is key for people doing inflow and infiltration studies. A lot of times people are looking at a lot of multiple or trunk lines or smaller lines that feed into a larger trunk line. They can now deploy a laser flow with a 2160 to capture that large trunk line flow for I&I studies. Wastewater treatment plants are going to be a big potential. Both the influent and the effluent can be monitored using the non-contact device. Influent pipes and channels within a treatment plant would also be another good application for the device. Hydraulic modeling. Again, when you put data into a hydraulic model, the data are only as good, or your model is only as good as the data that you put in there. You need to have accurate data going into the model. LaserFlow will give you that. Industrial monitoring. Harsh chemicals and environments. Don't want to get in there, especially industrial customers. Do not want to have to mess with their flow any more than they have to. They can install one of these, non-contact, not affected by harsh chemicals or the environment, and it's pretty much a plug and play. Turn it on, get it going, and leave it alone. Stormwater applications, another big one, primarily because of large debris. Stormwater can handle who knows what goes through those lines. Combined sewers, the same thing. You could have cars go down those lines, all kinds of debris, tree trunks, things like that. The LaserFlow will give you the ability to stay out of that location. Here's an example of a location application where they had real harsh chemicals, a tannery in Turkey, where they needed to measure something. In this case, they could use a continuous wave, or they could use the laser. Again, harsh chemical environment. A storm sewer application. We see more and more requests for this type. We don't want something in the water because of, again, debris, things like that. And storm sewers could have pipes that are very large pipes, especially combined sewers. You may have very low level flows that you need to measure, and maybe it's a 10-foot pipe that's got a couple inches of flow in there. If you're within 10 feet of the flow, the laser will read that. So you can mount it higher, and once that water level comes up, it will account for and read the entire range of that line. Submerged flumes. Seeing more and more applications for measuring submerged flume conditions. In this case, if you had to measure this, you would have a challenge. Typically, you would have to measure upstream and downstream and try to do some sort of a offline calculation using a submerged flume table. That's, accuracy would be suspect at best. This is also a fairly large channel. The laser would be a good option to mount up in front and be able to read during these conditions without having a sensor in the channel itself. Here again is the application in Turkey where they have a flume in there, but they do frequently surcharge this line. In this case, the signature meter really is a great selection because they have the ability of using the signature bubbler or ultrasonic to measure the flow in the flume, but they have the ability to use the LaserFlow upstream of that flume, and they can take it all into one device and read both the flow rates from each device, separate the analog outputs to each device as well, and get good, accurate flow data no matter what their site conditions require. So in summary, LaserFlow uses advanced laser velocity measurement. It is the only non-contact flow measurement system that can read below the surface. I will say that again, it reads below the surface. It is the only one that can read multiple points, and again we are doing multiple points below the surface velocity measurement. A very unique capability of this device. It is both a very precise and accurate measurement. We are going from tube televisions to high-definition big screen TVs with this device. It is also very easy to install and maintain. Very easy to set this up. It takes typically anywhere from a half hour to maybe an hour to install it on a permanent. Portable would take less time. Again, the benefit is we can install it very easily. Remotely, you can look at some of the diagnostics capabilities and tell if the sensor is mounted correctly without going back into that hole. Because we're using a continuous wave sensor on the submerged flow option, we are now able to get a better submerged flow measurement. It will now read not only what's happening in the invert, but it will transmit and read what's flowing through that manhole basically into the pipe using the continuous wave measurement. And we feel that measuring into that pipe is going to be a more accurate measurement of a submerged flow condition. And again, it's a very flexible platform. The device will work with anybody that has 2100 series, and we know there's a lot of you out there. Will be a welcome addition to your existing family. The 2150 will welcome it with open arms. The signature, for those of you that are starting your program or maybe have begun to expand using some signature meters, now we have the ability to use both with 21s and signature, providing you maximum flexibility on an AC-powered, permanently installed device. We are very excited about this new technology and are ready to answer any questions that you have. Feel free to contact us and look at the product at isco.com. You can certainly send any questions you have directly to me. My email is rdey@teledyne, teledyne.com. We look forward to working with you and expanding your flow horizons with the new LaserFlow. Thank you.